So that's really important. Thank you.
Okay, thank you. Yes, so, the whole week we've looked at, different aspects. I hope it's on. Yeah. Of different aspects of AI hardware. And, one architecture that was mentioned from the first class, but then, we didn't go over it further, is the Google TPU. And, on Colab, in principle, under some conditions, you can also get a TPU to do your job. And the reason I decided to go over this instead of something else that I had in mind is that, a couple of students actually asked me about systolic arrays. And we didn't really talk about systolic arrays, and the TPU is a systolic array, so I think it's a good opportunity. So let's do that. We did talk about, but I think this slide is kind of nice, that it explains a little bit the difference between kind of a conventional architecture, which is CPU, GPU, where the data flow is temporal. So, you have a memory and you bring things from memory and you put them back in memory and things happen, in different clock cycles. So time is kind of very important, as opposed to a spatial architecture where, things still progress in time, but there is a pretty clear progression in space. So, and, the systolic array is actually one of these spatial architectures. Again, this is a characteristics of all the lectures that I given. I give this historical, context. Again, systolic arrays themselves were not invented by Google for the TPU. They were actually invented, in the 1970s. There was a professor at Princeton named H.T. Kang. I think he didn't really invent them, but he wrote a book called Systolic Arrays, and he really proselytized them and popularized them. And there are, again, if you read H.T. Kang's book, you'll see there are many variations. But the idea with systolic arrays is that you have an array of processing elements, and they can have different topologies. So topology means how these processing elements are connected to each other. The most straightforward topology is this rectangular 2D array where the data moves in some direction, horizontal and vertical. But you can have many others. You can have something like here where you do still have horizontal and vertical, but you also have diagonal. And not only that, you can even have hexagonal. So, I'm not going to go into details. But the idea with systolic arrays is that for computations like multiply and add, when you have vectors or when you have matrices that need to multiply together, it turns out that you can, this C1 here will need to multiply with D1, but will also need to multiply with D1 too, and will also need to multiply with D1 3. So in the first cycle, these two come here, and then D1 moves down, C11 moves here, and then basically C11, is multiplied by D12, and so on and so forth. And you can do this computation, the data moves, and, it's a little bit like, that's why it's called systolic. Each of these is like a little heart, and, the blood vessels, transmit the blood, and the blood just flows through these pipes. And the nice thing is that there is no waste. So there are no cycles in which there is no computation, which is kind of amazing. And also there is no memory. The data just flows through this array. And I think there is, and basically, you map it to one of these. So here is an animation which kind of shows how this goes. So, and you kind of see the systolic part on how the computation happens. And, once the data has moved through the array, then, you have the final results. So any questions? I mean, this is, if you haven't seen this before, it's not going to be very easy to digest and ingest, but, you kind of can try by hand and see how these, multiplications actually make sense and fit. Yeah, sure. Okay.
Data is coming from this.
Mm-hmm.
Top data is going again
Mm-hmm.
bottom.
Yeah.
Top to bottom.
Yeah.
But there are different systolic arrays possible.
Yes, there are. Yes. Yeah.
How the data moves in H? If you
In what? H? H?
Type H.
Well, okay, that's something that, again, we can discuss offline. So yeah, I don't have it here. So the principles stay the same, like I said. So it has to do with the topology and it has to do with the scheduling of the data, yeah. Yeah. Right.
Direction of the data is only one direction.
Yeah. Let's talk after yeah, because I don't have a figure, and I think it's better to talk with a figure in front. Yeah, and this this is another kind of example of how the computation goes. So now we are getting to the actual TPU architecture, and here is the systolic array, which is literally like what I showed before. It's basically just a systolic array. And you see that in order to get it to work, there is a lot of stuff around. And again, for the systolic array, you need, and that's a little bit the question, you need this very magical time alignment of all the data to come exactly at the right time in the right place, because otherwise, again, the computation just happens, whatever. And if it's garbage in, you get garbage out. So for that, they have, and again, the data still needs to come from some memory. So there is a DDR interface to external memory. Then basically, there is you can think of it as a cache that sets up this systolic data. There is some control. And, again, because at the end of the day, the control is really just counters. Because, you just need to align the data one after the other. So, it's not a complicated, there is no branching, there is no ifs, everything but you still need to make sure that, they come at the right time. So, that's what's kind of here. Then, of course, once you do the multiply and add, you do need to have the nonlinear activation functions. So those are handled off the systolic array. And then, there is this pooling and normalization. And then, they go into this activation storage. And then you also need the interface to the host CPU. And that's basically through a PCIe interface. And this is the TPU version 1. So this is what they first presented. Then there are some more data about the number of bits, the memory. I don't think those are relevant.
So,
yes.
If you see the weights are being fetched with the memory bandwidth of 30 gigabits per second from clock. But if you look at the left, the data is being fetched with the 167 gigabits per second. So why there is a difference between the memory bandwidth these two interfaces?
Yeah. So let me think. That's a good question. So you get inputs times weights. So fundamentally, the reason is that I think you somehow I think you are going to use to reuse the weights more than just for. So if you think about how the so the matrices are not square. That's the reason. Okay. If you look at just one set of inputs and you get the weight matrix, so they are not going to be one-to-one anyhow. Actually, natively, if you just do one input, it's probably that the bandwidth on the input needs to be less than for the weights. But you have if you think about having an image and a kernel convolution, the image is much larger than just the kernel. So there are opportunities to reuse. Yes. Yeah. So, and now why, 167 and, 30, it's about 5, 6, I would say 6 times more. It's probably, again, a compromise, a trade-off, whatever, that. But yeah, fundamentally, you are always going to have much more data on the inputs than weights. Yeah. But yeah, that's a good question. And, I didn't think about it before, so I had to think a little bit about it here. Okay. Yeah, so, and you see that the weights and the data are kind of coming from different places. So they, there is some, yeah, some, yeah. So, and again, that's again part of, when we were talking, I think from the first lecture about the role of the compiler and, so that's where, this becomes a software issue. How do you do this so that all these units are always doing useful computation? Again, yeah, activations, we already talked about it. I'm not going to spend time. Again, there are some specialized functions that you need to do. And this is, again, this is for the VLSI people to see a floor plan. And you also get an idea about, kind of roughly the number of transistors. I mean, the good news is that, the systolic array, and that's what you want. Remember, when we're looking at GPU versus CPU, you do want that the processing elements that do the useful things to have a relatively large portion. And actually, this is less than what we saw for the GPU. But there are still so this buffer is actually quite large, and it is 24 megabytes. It's actually a little bit more, a third of the chip, just this buffer. And this, in some sense, that's what people complain about systolic arrays, because, for systolic arrays, the processing part looks very efficient. You only have, the max and the wires, and, it's really very compact and efficient. But you do need around it all these buffering to make sure that the data arrives just in time and, at the right, rate. This is actually a good illustration of that. Something interesting, and again, I almost didn't put this slide there, but I thought it's kind of interesting. So the lead architect for the TPU was Dave Patterson, who is actually a professor. He was on leave, and I think he still is on leave partially at Google. And this is, before he got the Turing Award with Hennessy. But he's one of the inventors of RISC. The original RISC, one of them was basically the MIPS architecture, and the other one was the Spark architecture. And one of them was done by Patterson at Berkeley, and the other one was done by Hennessy at Stanford. But for the TPU, again, so that's what I like. He's not religious about RISC. You use RISC when it makes sense, but you use, complex instruction set when it makes sense. And again, because the TPU doesn't really have to fetch instructions all the time. I mean, there's still some control that you need to do, but it's a very complex instruction. You say, okay, now I'm going to do this vector matrix multiply of that dimension. And then, for 1,000 cycles after that, it just does that computation. But, there are some, read the host, read the weights, do the convolution, and activate and write back to the host memory. And, again, to make sure that all those data are coming, at the right time, they have these FIFOs. So again, these would cost, transistors and area. And here is where you do the accumulation of the, of the results before you are done, and kind of the movement of the data, horizontal and vertical. How many people have seen the roofline model and know? Okay, not that many. Okay, so that's good. You are going to learn something very important. The roofline model, and this is also Dave Patterson, who kind of invented, well, not invented, but presented this. So the roofline model, in some sense, you can think of the roofline model as a way to quantify the memory wall. Because what the roofline model says, on the y-axis, you have the capability of the processing unit. How many gigaflops per second, maximum gigaflops per second, can that processing element do? Okay, so ideally, what you want is that your performance, the performance of your system, to be at that level. Okay. Now, what happens is that you, in order to do the computation, you also need to bring data from memory. And that's where the memory wall comes in. So in order for me to be at that peak performance in terms of processing, I need to have the data ready when the when the processing happens. And for that, there is this concept of arithmetic intensity, which basically means that for every data that I bring from memory, how many times do I use it? And the unit for arithmetic intensity is number of floating operations per byte from memory. So if I bring from memory, 1 byte, and I, and my, arithmetic intensity is 1, it means that, I'm using that 1 byte every time I'm getting it, but just once. On the other hand, if my arithmetic intensity is 2, that means that for every byte that I bring, I use it twice. So basically, I reuse the memory. And of course, that the more I reuse the memory, the less the memory wall The more I reuse the data from memory, the less the memory wall is going to affect me. So basically, if I'm on the right here, I have a high arithmetic intensity, which basically it's a reuse of memory. If I'm on this side here, I'm bottlenecked by the memory, because here not only I don't have a reuse, but I basically need twice the memory to do one operation. So that's why basically if I'm on this side, I am limited in my performance, not by the processor, but I'm limited by the bandwidth of the memory, okay? And that's why it looks this way. And it looks a little bit like the roofline of a house, so that's why it's called the roofline model. And again, these are two examples of two kernels, one that's basically limited by the memory bandwidth. It cannot do, it cannot keep up with the processing. And this one is basically limited by the compute, peak performance. This is an important concept for architects. And again, if in some sense, what you really want, and that's kind of my interpretation, you really would like, this is a good area to be in, okay? And the reason I'm saying that is that if you are here, your memory is over provisioned. Your memory in principle could be slower and come like this, and you would pay less. And of course, if you are here, your compute is over provisioned. Your compute could be here, and you would get the same performance. So that's why, in some sense, the optimal place to be is here. And any questions about this? I think this is an important concept. Oh, okay, not right now. Of course, the reason he kind of presented this is to show the difference in the roofline models for, kind of the three competing architectures, CPU, GPU, and TPU. And I guess CPU is this brown one. The GPU is this red one, and TPU is the blue one. And guess what? Kind of what I told you, the TPU happens to be in an ideal place because it has this very high compute capability, and at the same time, it has a lower memory bandwidth, and kind of doesn't pay the price of the memory bandwidth. And on the other hand, if you look at also the difference between CPU and GPU kind of explains why GPUs have taken over. Because GPUs are better overall, both in memory bandwidth and in processing. So the CPU kind of, cannot even compete. And again, there are all these points here where the TPU and of course, these are kind of one-to-one. So for example, I guess this is CNN 0, which is that one there. And then CNN 0 for the, yeah, I'm not sure. Now I'm confused. Why is there a CNN 0 here blue? Yeah, now I'm a little bit confused. So based on the colors, yeah, I'm not sure.
So I believe that CNN 0 was implemented on one hardware and the CNN 1 was implemented on another hardware, and then they are comparing the performance.
Yeah.
I just guess, I'm not sure.
Yeah. But anyhow, I think the message is there. Let's not worry too much about this. And again, here are some reasons for, and this is kind of the important part where it's kind of the percentage of the maximum instructions per second. And the TPU has kind of the largest, and let's see. So depending on, yeah. So what they are looking here, and this is related to the latency of a response. So if you want a fast response, in this case, 7.2 milliseconds, 6.77 milliseconds. So that's what Google considers, good enough. Then, both the CPU and the GPU are kind of struggling to get that response. When the response, basically, what this 42% means that only 42% of the time it can meet that latency. So in order for the CPU to meet 100%, the latency that it can meet with 100% probability is 21 milliseconds. This one, the 100% is not that bad, actually. And, the TPU is a little bit, but the point is that, if you look for the 80%, so the distribution is very skewed, I guess, between TPU and GPU, for example, because GPU, it means it has a relatively long tail in the distribution, because, this looks pretty good, but then, to get, 7 milliseconds, it's, just 1/3 of them meet that. Now, again, here you can argue that, 1 millisecond or 2 millisecond difference is not that important. So I'm not sure that this graph really shows a big advantage. It's a little bit manipulating the data, frankly. And of course, this is just the first TPU, and in some sense, probably because these are not very solid arguments, that's why GPUs are really dominant and not TPUs are dominant. So, well, this is another important thing. So these roofline models are all logarithmic. So differences that look small here, when you look at them in linear graphs, it's even more dramatic. So TPU is this one, and everything else is here at the bottom. So yeah, in that sense, this is a little bit more dramatic. Now that was the first TPU, and by now they are already at the 5th generation. And I'm going to go very quickly over kind of differences. So the one on the left is the oldest, and the one on the right is the newest. So TPU v2. So it's all about making them bigger and bigger. So TPU v2, they went to HBM memory instead of DDR, and that's kind of to help with their own roofline. So their bandwidth was not that great. So arguably they felt the need to have higher bandwidth, and they doubled the number of systolic arrays. And this is the TPU v1, and again, I'm not going to go into details, and TPU v2. So that's also kind of interesting. So this is a little bit like what happened with GPUs. So they went from having a relatively heterogeneous architecture where the activation and the accumulators, they were different memories to have just one unified memory. And yeah, I'm not sure. There must have been some units, and then they created a special vector unit. And again, this is the systolic array and the HBM, and then some interconnect. The systolic array is larger; it's 128 by 128 now, and they are also introducing. I'm not sure again how many people have heard of B-float. B-float. Yeah. So it's a brain. So B comes from brain. So they basically took the standard IEEE 16-bit floating point number representation, and they changed. I think they made the mantissa smaller, and if I'm not wrong, I hope I'm not wrong. Maybe the other, but no, I think that's the way. So they made the mantissa slightly smaller and the exponent slightly larger, and they called it B-float 16. And actually, that's what it is. So this is sign bit, exponent, and mantissa, and I don't know what it's for the standard floating point. They did, some more about matrices. They can do now transpose and reduction and permutation. And there is some interconnect now because they have 2 units, and they also can connect multiple of these TPUs together through the link. And the floor plan, looks much messier than before. And again, it's mirrored. Yeah, sure.
This interconnect router is within chip is what you're talking
about? Yeah, it's right here. And they also, so it's basically so the first TPU was kind of, more like a standalone accelerator. Now, because all these models are becoming larger and larger, this is, not only for the TPU, for, everything, GPUs, whatever, they need to be able to assemble large numbers of accelerators that can work on the same problem. And for that, you need very fast, interconnect. So basically, these are to connect, multiple TPUs together. And
the field that you showed 2 slides back, there was somewhere I saw a number 500 Gbps or something.
Yeah, I don't know.
No, ahead, like just around that particular slide only. TPU V2 somewhere around that. Ahead.
Yeah, I don't know.
After that?
Well, after that, we didn't go yet. Yeah. Let's take it offline. Yeah. Oh, maybe here. Yeah. 500 gigabits. Yeah. Because again, when you communicate between different, so this is an off-chip communication link. So yeah. So here is the B-float versus the float. So like I said, the mantissa has fewer bits than the IEEE standard float. And, the exponent has more bits, and, based on trial and error, I guess they figured out that this works better for AI applications. TPU V3, so they have a V3. Again, just upgrades to the HBM. I think the previous one or 8 gigabytes, now it's 16. And now they have 2 matrix units in each of the 2 halves. They have, again, they have the interconnect link there. And again, this is an incremental, change compared to V2. The frequency is slightly, the bandwidth is slightly higher, the capacity, but other than that, it's pretty much the same. But again, the big thing is moving, scaling out. So you may have heard these terms from, computer server kind of center. So there is the concept of scaling up and scaling out. So, you go up in a rack and you go out to other racks in order to have, basically nowadays, and again, you may have heard this, but nowadays these data centers are supercomputers. In the old days, a data center was an assembly of, many computers that were working, on different problems, to serve a lot of users. But nowadays, they also can work on just one problem. And that's kind of a characteristic for a supercomputer. So they really are like a supercomputer. And again, it's necessary to have these, and here is where the hundreds of gigabits per second connections are necessary to create this torus network with those links of multiple TPU chips.
The reason I asked that question is because even in the latest ISSCP paper, I never saw someone going above the link rate of 224 gigabits per second unless it's an optical link or something.
These are actually, I think, optical. Yeah. Yeah. And again, I think I showed you something like this for Cerebrus. So again, you no longer care that much about the individual, and these are water cooled, microfluidic cooling. So yeah, all these very, powerful ways to get a lot of performance. So again, TPU V2 still had heat sinks with, fans. TPU V3 is already doing microfluidic cooling. And again, this supercomputer, they even call it that, it has 1,024 chips, and you get more than 100 petaflops and 32 terabytes of HBM, and again, these are kind of the speed ups that you get. And again, it's what you want to see, no Amdahl's law, at least for some of them, in terms of the. And then there is a TPU V4. This is 7 nanometer, 275 teraflops, 200 watts, and this is chiplets. So you can recognize the HBMs, and they are all in a package. Again, optical switching. 4,096 chips. Sharing the memory. And this is the architecture. They are still having kind of 2 compute units, but then they have much more for the memory and the interconnect. And I guess this is a comparison of the 2, and you get 2 times the performance for lower power. And of course, by now they already have V5. I don't have any slides on version 5. And I think we are done. No, there is still some more. Yeah, so this is the board, which has the color-coded microfluidic coolings. And this is the rack, and this is the system. And then now it's no longer a torus, it's a cube, the interconnect. And the optical circuit switch is kind of crazy. So basically you have the optical fiber coming here, but then the switching is through you know, what do you call this? Basically with mirrors. Free space. So it's a free space kind of switching where, you know, you have MEMS arrays, microelectromechanical systems that have, you know, these are used actually in the projectors. So you can modulate the direction of the reflection with that. And yeah, it's a pretty crazy. And you know, this is how the